Welcome back to the Mechanics of Solids lecture series. We're looking at examples for how to solve shear and bending moment diagrams using a set of simple rules. The next example we'll look at is a cantilever beam with a series of loads acting on it. To save some time, we've already solved for the reaction A sub y acting upward and the concentrated moment at the fixed support acting in the counterclockwise direction. Note that because we're using numbers here, on my shear force diagram I'm indicating the units in kips, and my bending moment diagram is in units of kip feet. Now let's start by drawing the shear force diagram. Starting with end A, because the reaction 108 kips acts upward, the shear force diagram jumps up by a value of 108. Because we have a distributed load acting from point A to B, we know the shear force is going to be linear from that region, and the distributed load acting downward, the shear force is going to decrease. To calculate the value at B, I take the value at A minus the area under the distributed load diagram, which would be 4 times the distance, 12, and that equals 60. So I'll draw the diagram linearly decreasing from A to B with a value of 60 at point B. Now from B to C there's no distributed load acting, so the shear force is constant. We extend the line straight across, and finally at point C we have a 60 kip load acting downward, so the shear force diagram jumps down by 60. So going from B to C, 60 minus 60 equals 0, and we check and confirm that the shear force diagram does come back to 0. It's always important to do this check. Now for the bending moment diagram, we start out at point A. Since we have a concentrated moment acting in the counterclockwise direction, the bending moment diagram jumps down by that amount, by 1588. Okay? Now from A to B, the shear force diagram is linear, so the bending moment diagram slope is going to be quadratic. Shear force is positive, so bending moment will increase, and we can calculate the value at point B by taking the value at point A, negative 1588, plus the area under the shear force diagram. To calculate the area of the trapezoid, I'm going to calculate an area of an equivalent rectangle that has a magnitude equal to the average of the values at point A and B. So that would be 1/2 times 108 plus 60. That's the average value of the trapezoid times the length of 12, and that is equal to negative 580. So that's our value at point B. It's something like this. Now, we know it's quadratic from A to B. We know that because the shear is larger at point A than at point B, the slope is going to be larger at point A than at point B, and so my diagram is going to curve kind of like this. So value at point B, 580, and here's my diagram. Slope is quadratic. The slope does not come back to 0 at point B because the shear force didn't come back to 0 at point B. But it is the slope is less than the slope at A, and our bending moment diagram is negative in that region. Okay, finally from B to C, we know that the shear force diagram is positive, so bending moment will increase. It's constant, so bending moment will be linear, and we can calculate the value at C by taking the value at B, negative 580, plus the area under the shear force diagram, which is 60 times 8, and this gives negative 100. So I have my shear force, or my bending moment diagram, varying linearly from negative 580 to 100. Sorry, I like to put the magnitudes on the diagram, from point B to C. And this is, just to be sure, this is linear. Now finally at point C, a shear of a bending moment of negative 100, plus we encounter a concentrated moment of 100 kip feet acting in the clockwise direction. It's going to cause the moment diagram to jump up by 100 and therefore come back to 0. And I always want to see that check. And looks good.